Hello everyone and welcome to FusionEPTalks, a student-led webinar platform for sharing knowledge about nuclear fusion, science and engineering. I am Jose and I would like to introduce our speaker today, Michele Marin. He's a postdoc student. He already come from the École Polytechnique of Lausanne in Switzerland. He are going to speak us about the understanding, the title of the talk is Understanding the Plasma with Integrated Modeling for the Plasma Physics. He will tell us about the plasma dynamics and the simulations he have done and how he can speed the process for take the modeling of the plasma, and he will let us know more about his work. Also in the talk, he will include some integrated modeling and validation of cycles and examples of applications. Okay, everything's okay. Yeah, I will stop sharing already my screen to let him the voice. Please, Michele.
Thanks a lot for the presentation and thanks for inviting me here. But today I wanted to talk a little bit about integrated modeling. I feel that is a slightly under-advertised tool in the fusion community. So I wanted to take this opportunity to introduce integrated modeling and to showcase a couple of applications and the uses that you can do of these tools. So content-wise, I will introduce this integrated modeling. Then I will take a little bit of a detour to talk about gyrokinetics, which can be viewed as one of the components of this integrated modeling. And I will explain how. And then I will use this to explain what the validation cycle is to improve these kind of tools. And I will also talk about the importance of reduced models and what they are. And then in the second part of the talk, I would like to present some examples of the uses of the integrated modeling I did during my PhD, and will be some steady state, do the dynamics, and then some comparison between different experiments and the modeling to experiment. So this will be it. And without further ado, let's go to the content. And I will start by introducing the integrated modeling. And I want to do this by starting with some motivation. So why do we do that? Of course, the end goal is to be able to predict what will happen in future reactor, so the behavior of future reactors. And if we had only one experimental machine, that would be relatively easier. So you could envision empiric model or even a neural network. And as long as you are in the parameter space you're familiar with and you're already tested, those kind of models should behave pretty well in predicting the experiments. But as soon as you have to extrapolate to something really different, those models start to fail. So one of the tools you can have is, for example, scaling laws. Scaling laws work with, for example, a set of parameters of variables. And here, one example is the engineering variables, the electrical current, the magnetic field, the density. Basically, the quantities that are connected to the characteristic of your machine and the quantities you will set up if you were in the control room and you were designing the experiment. Or you can use dimensionless parameters, which are parameters that matter for the turbulence. And those are usually associated with the diffusion coefficient. And with those variables, you build a function. And then this function will produce usually a 0D variable. Like here we have the energy confinement time, which is basically a measure of how well your energy is confined in the plasma. You build this function, and then you compare these with a database of experiments. So in the figures you have here, you have each point represents a different experiment. And once you start to have a lot of experiments and in a lot of different machines, you can span a large subset of the parameter space, so various values of all these parameters. And building this database and fitting this function, which usually is a power law, you can try to reproduce the experimental the experiments. And then you can use these to extrapolate what will happen in different conditions. One problem in this approach is, for example, that you can see the scattering of the data is quite large. This is a logarithmic scale, notice. And this scatter also means a large error bar. So the error bar for our prediction or what will happen in future machines will be quite large. And also the other problem is that the underlying assumptions for this kind of scalings is that the physics, the underlying physics, will not change substantially from current machine to future machines, which is not necessarily a given. So here you can see ITER. I'm sure that the participants and those who follow this channel already know, but ITER is a large tokamak, the largest tokamak that will be built, that is being built in the south of France. Is supposed to produce 500 megawatts of fusion power from 50 megawatts of input. And one of the reasons why it's so complex to model, as it's very complex to model current experiments, is that it will be composed by a lot of different parts, different subsystems that will interact with each other. So for example, here, the magnetic coils will produce some magnetic equilibrium where the plasma will be confined. And then we want to heat that plasma, and we will do it with, for example, radio frequency heating or neutral beam injection. We will refuel the plasma with particles, with frozen pellets, at least in ITER. And then these heat and particles will be transported out of the core by turbulence, and will, in the end, hit the walls, ablate some of the material, and produce impurities, which is whatever is not isotopes of hydrogen. And these impurities will cool the plasma, and all these subsystems will interact between each other and will interact non-linearly. So it's a really complex system to try to analyze. One way you can think about doing this, and this I will give the example for turbulence, is to try to use as few assumptions as possible to have a really complete model, like a really complete description of your plasma. And the theoretical framework for turbulence that was developed to do so is Gyrokinetics. And the most complex simulations that you can envision with Gyrokinetics is, for example, global simulations where the whole volume of the plasma is modeled at the same time, full F, so with the full distribution function, multi-scale, which means that you're looking at both the electron and the ion spatial scales at the same time. And this is for the turbulence. And then you could envision to do the same, for example, for the radio frequency heating, very complete model for that, very complete model for the neutral beam injection or for the equilibrium with the magnetic hydrodynamics. And then you combine everything together. That would be a really accurate representation of the plasma, but the problem is that would be monstrously slow. And with monstrously slow, even just the gyrokinetic part can take years on hundreds, if not thousands, of course, for each simulations. So this is okay if you have to do one simulation, but usually for applications, you need to do multiple simulations. You want to do scans of different parameters. You want to do optimizations. And even you need real time, for example, for control purposes. So how do you go from years to real time? I will not tell you how to go until real time. It can be done, but I won't touch it here. But I will try to explain how to go to hours or maximum days for a single simulation. And these, you guessed it, it was in the title, it's with integrated modeling. But what it is basically you have a different model, a different code that models all the different, each different subsystem of the plasma. So you have one code for the equilibrium, one code for the impurities, one code for the turbulent transport, and then you put them all together and you let them talk with each other. So you basically iterate with time. Each time you evolve the full system, you run all the modules. And then you let the output of one code be the input for the other, and evolve all the plasma profiles, the plasma parameters. By doing this, basically you are capturing the same complexity that is in the experiment, but in the modeling. And you can explore a lot of physics that is created by this interaction and would not be possible to explore otherwise. So a little bit of a friendlier picture of the same problem. You have the same components that I was explaining before, but now each of them is described by a different code. In the end, what you end up doing is to leverage the symmetries of the plasma to turn a 3D problem in a 1D problem, and you solve a set of coupled 1D partial differential equations. So this is what, for example, JINTRAC does. It solves the continuity equation for energy, momentum, and particles. And then it evolves the plasma and it tries to reproduce the experiments. One very important, crucial quality that these codes have to have is to be fast, because we can't wait years. So these codes need to run in seconds, maximum 1 minute. But how do you get from the very slow codes to these fast codes? You use reduced models. So for the turbulence, for example, one code that I had to deal with a lot during my PhD is QuaLiKiz, which is a quasi-linear model. And the idea of building this reduced model is you use the large, more complete codes, you run them, and you try to understand what is important, what is really important, and what is ignorable, or what is where you can make assumptions to ease the problem. So here are some of the assumptions that are made in QuaLiKiz. And the key word here is quasi-linear, which means that you only evolve the linear part, which is the fastest part to calculate. And then the nonlinear part is just fitted to nonlinear simulations, a few nonlinear simulations, depending on the turbulent regime. So this is how you can build a reduced model. And then this will run much, much faster. This runs in seconds. And of course, there is a trade-off here. What you gain in speed, you lose in accuracy. In the end, you want to end up with a code that is fast enough and accurate enough. And then the enough here will really depend on the specific application. For example, easy rule of thumb that you can imagine for accurate enough is when it's inside the experimental error bars. And then one of the characteristics that make integrated modeling so nice is that since you're evolving the physical quantities, so the current, the temperature, and the density, you can very easily compare your results with the experiments. And so this creates kind of a validation cycle. This is from Francis Casson. They presented it for the first time, the TTF in 2018. And this validation cycle consists in first running your integrated modeling in various experimental conditions. If it works, then it's perfect. We can predict that particular experiment. If it doesn't, you try to understand, okay, but where in the quasi-linear model, or even where in one of the reduced model is it failing? Then you can compare with more complete model, with the nonlinear model and the higher fidelity models. And then you try to improve your quasi-linear model with the information you got from the more complete models. And then you put it back in integrated modeling, run again, and compare with experiments. And in the end, you will try to end up with a set of codes that work in the conditions you are trying to use them for. So this was an introduction on what integrated modeling is and how it works. And now I'm going to showcase some examples on how it was used and how I used it during my PhD to try to discover some physics and reproduce some experiments. So the first step that you can do, the first thing that you need to do is to try to reproduce steady state plasma. So you just take, you average the experimental data over a time window that is long enough with respect to the time scales of your plasma. So you can define it as a steady state. And then you relax the integrated modeling, you let it run for as long as it needs to. And you compare the profiles that come out from the modeling with the ones that are you measure from the experiments. This kind of 1D plot that you can see here are the plots I had to deal during PhD. It was my life for a while. The x-axis here is a coordinate which is connected with the magnetic flux, but you can very easily imagine this as a radial coordinate. So in the middle, in the at 0, you will find the middle of the plasmas, the axis, while on 1, you can find the last closed flux surface, which is basically the last surface where if you have a particle that is following the magnetic line, it will not go to hit the materials. You could, in principle, and this is available in JINTRAC, go up until the materials and model up until the materials. This is called core edge coupling, but it is very complex, still fairly slow. And actually here, we will not even model this region, which is the pedestal, where the gradients are really steep. And this is because a fast first principle model for the transport in the pedestal is still not really available. But we will try to model whatever is inside 0.8. So basically, we take our boundary conditions here, and we model whatever is inside. We'll try, just to be sure that we are not right for the wrong reasons, we try to model different multiple channels at the same time. So we model the density and the temperature and the angular frequency, everything at the same time. And you can see here that actually the integration modeling and the experiment tend to agree pretty well in these conditions. Important thing here is to notice that in principle, these integrated modeling does not need the experimental data. So if you had the pedestal, you could have predicted these profiles before the experiment, in principle, with a few caveats. Then once once you're able to model the steady state, you can try to model the evolution. So here I'm showing the evolution of the plasma, and in particular, what we were trying to study here was the injection of pellets. So you can see that the density increases around 0.8, so towards the edge of the plasma. And then the profiles relax and the temperature also decrease and then increase again after the pellets, because of course the increasing the density also is cooling your edge, your pedestal. And here we were trying to see how the fuel was penetrating into the core. So we had pure deuterium pellets in pure hydrogen plasma, and we were interested in the speed for the deuterium to go into the core. And that will be relevant, for example, when we have to fuel ITER or reactors with pellets. And then with these kind of tools, we are also running QuaLiKiz to predict the transport. So you can look at the turbulence, which is calculated for each time step, and see what kind of turbulent regime you're in. And if the experiment, if the modeling is similar enough to the experiments, you can be reasonably comfortable in saying that the turbulence captured by QuaLiKiz is actually what is happening in the experiment. So just to be extra sure and to show you one example of the validation cycle, here we took the parameters from the integrated modeling, and we run both QuaLiKiz and GIN, which is a higher fidelity code, and we compare them. So here, this is an example of nonlinear fluxes. In blue, you have particle fluxes, while in red, you have heat fluxes. The electrons are in the first row, and then you have the hydrogen and the deuterium, and the columns represent the main species, and then a trace that was added to be able to divide the diffusion with the pinch coefficient. And the important image here, the important picture, is this one, where you can see that you have a very large deuterium influx, a deuterium particle influx, which is very similar with what we observed in integrated modeling with QuaLiKiz. The experimental observation indeed was that the field was penetrating very fast into the core. So we confirmed it both with integrated modeling, the quasi-linear model, and then we confirmed that the prediction, the correct physics was being captured by comparing with these nonlinear simulations, which are more complete. Another application on integrated modeling is on comparison between experiments. Here, for example, what was observed experimentally was that the confinement improved after the injection of neon. One wants to try to understand why this is happening. And in the experiments, you kind of have the problem that you can't really change one thing at a time. As soon as you inject neon, you have the pedestal that is changing, the rotation profile is changing, the impurity composition is changing, and it's really difficult to isolate the effect of each of these changes. But with integrated modeling, it's just simulation, so you can do it. So this is what we did here, for example, and we were able to show how most of the improvement actually came from the change in the pedestal, that they observed reduced Ki, so ion heat transport, was mainly due to the increase in rotation and the decrease shear, and that the decrease instead in electron heat transport was mainly due to the change in impurity composition, to the increase in the impurity composition. So this is another topic area where integrated modeling can be really useful. Of course, we'll step back a second. You first need to be sure that you can model both your experiments. You need to be sure that you can model the unseeded and the seeded discharges. And this is what is shown here. So we can indeed, the experimental data and the model for both experiments are a reasonably good agreement. Then my last example would be that the integrated modeling was also used as a preparation, as part of the preparation work for the recent DT campaign that happened at JET. And the idea there was to try to predict how the experiment in DT would look like. So first, you need to be able to show that you can reproduce current experiments. So we took an experiment, the top discharge in deuterium, and you can see the experimental data here in red. And then we used integrated modeling to try to reproduce that particular discharge. And these are the orange lines. So you can see the ion temperature is very well captured, and the electron density is slightly overestimated. And this translates in a slightly higher predicted neutron rate. But then now we know that the modeling is maybe a little bit overestimated, but can reproduce these discharges fairly well. And then we can try to predict their equivalent in deuterium tritium with higher power. So this is the result of that kind of modeling. Indeed, in the actual experiments, we did not had 40 megawatts available, which would be the orange line here. And the prediction for that full power would have been around 17 megawatts of fusion power, which is quite a lot higher than what was actually achieved. But in the experiment, we only had around 34 megawatts. And this is not too far from the red line here, which was the experiment that we reproduced, and just changing the pedestal with a scaling, the DT mix, and the heating power. So I hope that I was able to convince you that integrated modeling is a powerful tool to predict, to reproduce and then predict the experiments. We can use the validation cycle to continuously improve the capabilities of our modeling. And these accurate and fast models we want to end up with can help design and then control the future experiments. So with this slide, I am concluded, and I'm open for questions.
Yeah, we will start now the questions and answer time. And I have a question, Michele. I think it's yeah, quite basic, but I have this question. I guess because already you have compared the results on jet experiments with your integrated modeling, but I guess, well, for example, for predicting the the densities and temperatures in ITER, it will be affected because of the volume of the plasma. That's right, no?
Yes, indeed.
So for bigger volume, it means could be less accurate the integrated modeling.
So a bigger volume should not impact the prediction that is accounted for inside the models. But ITER indeed will have a few features that are difficult to predict with current models. Especially for the pedestal region, which would be slightly different than the pedestal region in jet and other machines. For example, a difference in jet is that one is peeling ballooned and the other one is peeling limited, and the other one is ballooning limited. Mm-hmm. And for the core, which is where most of my focus was, we expect the models to behave fairly well. The major difference that you could see there is with the electromagnetic stabilization, which is included kind of ad hoc in QuaLiKiz. Mm-hmm. And then it's not really easy to know in advance how much or if the stabilization from the alphas will be comparable to the stabilization that we have in jet or in other machines from fast particles.
Yeah, because we'll be more alphas in case of ITER.
Yes, so that would be one of the
hopefully.
Yeah, hopefully, yes. That would be one of the major differences, at least for the core modeling. The volume, the fact that you have a larger volume, of course, will result in different behavior, but it should be consistently predicted by the integrated modeling.
Okay, perfect. Okay, we have a question from Adam Parrott. Okay. Let me see.
Hi.
Yeah, Adam. Yeah. Can you go?
So yeah, my question is, it's about how does the integrated models that you've presented relate to, or do they feed into the development of like real-time control models? Because that's the sort of area I'm kind of curious about. Perhaps there's ways you can use your high fidelity models and train predictors that you could use in a control application, for example, or maybe there's other things.
Indeed. So this is exactly what is done. I said that I would not get into really how you get to real time, but I will get how to get to real time now. So basically what you do is, once you have a model that is fast enough, now QuaLiKiz is fast enough. In the future, maybe even linear gene will be fast enough. you can build a database of simulations, and then you can train a neural network on the database. And the neural network will basically give you the same or kind of the same answer, but in milliseconds. And then once you start to have these reduced models with neural networks or analytic calculations, you can really go down to real time, and you can start to think about control application. This is done actually here in EPFL with a code that is called Raptor, which is real-time capable.
Okay. Okay, yeah, we have here another question in the chat. Thanks, Michele, for the nice lecture. I have a simple question. This is from Yuri Asnis. What languages do you usually program?
So I personally use mostly Python, but I'm mostly doing simple input outputs and plotting tools. The ones that really develop the models usually use or again Python for the coupling or Fortran. And Fortran is used because of the high capabilities of allocated and deallocated memory, so it can be really, really fast. And when you need to run these codes thousands of times, the speed starts to really matter.
Okay. Okay. Well, Adam, do you have more questions? Let me see.
No, sorry, I couldn't reply earlier because I muted myself. But thank you very much.
Sorry,
That was a great answer. So thank you very much.
Okay.
Yeah, you even have one of the developers of these neural networks in this chat, which is Carl. I see David has a question.
Yeah, I mean, thank you very much for the presentation and for giving a chance to give a question. I'm really sorry I joined late, but I was working, I was involved in integrated modeling for a very long time, maybe 15 years or maybe more. The question is the predictive capabilities of different models. There are different models. So did you validate these predictive capabilities on TCV, for instance? So you have some, for instance, you plan TCV as a plan to, let's say, make given short type of shots, so just scenarios for the next year, 2023, but you can try to make the simulation, let's say, 1 year address and more. Are you interested to make, let's say, checked predictive capabilities on, let's say, new machines like Compass Upgrade, which will be in operation before it, at least we hope, and to just check, so can code, the integrated model you are speaking, can really have good predictive capabilities?
Yes, so for multi-machine validation, that is now within a program in Neurofusion, which is TSVV11, there is the plan to really go for systematic validation of a lot of experiments in various machines. So Compass will be included in this at some point. And then for what concerns TCD, well, this is my job right now. So I'm trying to model, for now, omic discharges and the ramp up of omic discharges with integrated modeling. It seems to work fairly well, but I'm still working on it. So I don't really have results to show to an audience yet.
So to be clear, you are a member of TSVV11?
Yes, I've been signed in.
Okay, thank you. Thank you.
Okay, thank you, David. Well, and we come now with a question of Abdel Kale Basandi. Okay, I will give him the word.
Okay, thank you, Michele, for the presentation. I have a question here, but it's not. I'm sorry, it's not related to the topic that you are talking about. I am currently seeking for a master program in the production of energy from the nuclear fusion and the plasma. So So I'm asking you about some advices that can help me. What courses can I take to develop myself? And also what skills that I need from programming language and the simulation software. I already studied physics. I take a lot of courses in plasma physics and in nuclear physics.
Okay, so if you know enough about that, of course, I mean, the plasma physics is important. And then plasma physics specifically for nuclear fusion. There are some master classes. For example, at TUE, there was a very nice master class, and there are some summer schools that you can participate. There are intensive summer school exactly for fusion. And then, yes, I do advise to try to learn how to code properly. I'm still not great at coding, and it's something that I'm self-teaching. So that if you can do it in a structured way already, will probably be really useful to your career. And the language is probably Python, Fortran, C++. Lots of languages are used in the fusion community, so you need best practices more than a specific language, I think.
Yeah, I already did my project in nuclear, so I used Fortran, and also I know C++. I'm now currently trying to learn more Python.
Mm-hmm.
And I take a summer plasma school. I think it's sponsored by the Fusion Europe.
Yes, those are really good.
It's in Port Said, yeah, in Egypt. And I take a workshop in nuclear fusion and the plasma also. So yeah, which advice did you give me to be more focused in plasma physics and to obtain an opportunity for a scholarship in that career?
For the scholarships, you have to look around what is available. If you already took enough courses and you already know the physics, you can already start looking at papers and try to understand what you're interested in. Plasma physics is enormous, and fusion generally is an enormous field. So first, I will try to understand what you, which subfield you want to specialize.
Yeah, I will take advantage also for promoting the Master of Fusion European program. You can also check it out.
Okay, thank you. Thank you, Michele. Thank you.
Okay, well, now we have another question of the chat. Yeah, we can give this for later. We have another one here. Yeah, Matthias Aradi. Yeah, you can talk now.
Yeah, hello, Michele. Thank you for the nice presentation. You mentioned that you have some comparison modeling with the real measurements, and my question is about what kind of physical parameters or measured parameters did you use for initial parameters for your modeling?
So this you could see. Let's see if it works. Yes. For example, here is a very clear example. The initial conditions for the modeling are just the fitted profiles, and then you want to let the modeling evolve until it reaches a steady state. So you kind of have, you compare a steady state in the experiment with a steady state in the modeling, and you should be comparing apples with apples. So you just start from the experimental profiles.
And did you use some other input parameter like how should I say, like the heating power or something like that?
Yes, yes, of course. You have to impose, for example, okay, this modeling, you need to impose the boundaries of the equilibrium, which is because this the equilibrium code that was used here is not a free boundary equilibrium code. So you still need the boundary from the experiment. For the heating power, you don't need the profiles themselves, but you do need to know how the NBI was, the setup for the NBI, We have Pencil, which is a module that is predicting the MBI and the source, the heat source and the particle source. But of course, you need to put the experimental parameters there, the experimental energy of the beams to get the correct source. And then another thing that you need to set from the experiment is the impurity composition, at least at the edge, because since you're not including the edge, so you're not doing core edge coupling, the impurity composition needs to be imposed from the experiment.
Thank you very much. And how do you see how much hard to implement some other experimental devices like other Tokamaks, for example?
Once you have the geometry, it's not too difficult. This integrated modeling, it was the JINTRAC, the integrated modeling suite, was developed at JET, but it doesn't support only JET. It can support JET, DCD, West, East, I think JT60 and a few others. So it's fairly flexible that way.
Thank you very much.
Okay, now we come with another question in the chat. This comes from Hadi Barati. Thanks for the nice presentation, Michele. Is there any numerical computation involved in the integrated modeling? If so, what is the least numerical resolution to have reliable results by the integrated modeling?
So there are a lot of numerical computations. The numerics of the integrated modeling is fairly complex. So you have to have all these codes that you see here talk with each other and not produce numerical instabilities. I am not an expert on the numerical schemes, but of course you have to have time grids and spatial grids which are not too large. So what we usually use for core integrated modeling is a spatial grid of around 50 points for the radius, 25 points for QuaLiKiz. So QuaLiKiz is calculated on 25 different spatial points. And then the time step is usually around 1 milliseconds. And then the time step is adaptive. So we'll try to find the correct time steps by itself. For example, when there are strong transients, and this was the case during the pellet experiments, the time step was going down a lot, up to E-7. So microseconds, even if that's not really physical, but really there for numerical reasons, that can slow down the simulation considerably. But then the exact, this is what works for JET. The exact grid parameters that we work on other machines is a little bit of trial and error.
Okay, well, we have last question from Ignace. Do you think you can model plasma instabilities using your approach?
Okay, it depends on what you mean with instabilities. So big instabilities is intended as turbulence, yes. Magneto-hydrodynamic instabilities can be included. Some can be included. For example, SOTIT can be included, and ELMS can be included. But other, in principle, they can be included, but that can prove to be a little bit of a challenge that I haven't tried too much magneto-hydrodynamic, because it really slows down the simulation and you would do it if you need it. But in principle, yes, it can be coupled.
Okay, perfect. Well, I think we have not more questions for a moment. Yeah, thanks you, Michele, for the nice talk. And